Alright everyone, today I'm going to present you with a great video on how to rotate AVL trees, and we'll also get into the theory of AVL trees. So why don't we actually start there with the theory of AVL trees. Why do they exist? What's the purpose of them? Let's get right into it. So to begin with, we have AVL trees. A lot of people get confused by this concept. What is it? Well, an AVL tree is just a binary search tree. So you can imagine that it's just a binary search tree that is balanced. All right. So what that basically means is that it doesn't have a height difference of more than one for the left and the right subtrees. So balanced means that the height difference between a left and a right subtree of a root does not differ by more than one. So initially, you may be thinking to yourself, what does that even mean? Well, I think it's best if we look at a few examples of different AVL trees or different binary search trees and tell if they are balanced or unbalanced. So let's take a look at that. So I'm going to take a look at a couple of examples. All right. So let's first take a look at an example of a regular balanced tree. So I'm going to switch my colors here, make some pretty color variations between balanced and unbalanced trees. We're going to label this with a nice pretty blue. We can start off with the D as the root. We have B to the left. Remember, this is basically a binary search tree. So you got to remember that the left subtree or the left child has to be less than the root and the right child has to be greater than the root. So we're going to continue to maintain this property of a binary search tree. And so we have BAC in the left, that's less than in the correct order, and on the right we could put like node F, E, and G. And so we could see that this is balanced because the left subtree at each point in the tree does not differ by a height of more than one than the right subtree. So we can see that every node, if we start up from the top, D over here does not differ between the left and the right subtree heights by more than one. Same thing with B, A, F, C, E, and G. Everything is all good to go. So why don't we take a look at a unbalanced tree. So let me get out this other pretty reddish color. Let's use this one over here. So unbalanced tree. So what does an unbalanced tree look like for AVL trees? Well, if we start off with A at the top and we try to insert C in next, then we know that C is going to be the right child of A. And then if we insert B, that's going to be the left child of C. If we insert E, that's going to be the right child of C, but D is going to be the left child of E. If we insert G next, that's going to be the right child of E, and then F is going to be the left child of G, and then we can insert H, which will be the right child of G. And based on the way that I insert them into the tree, a binary search tree would put it in this order if I inserted exactly how I just told you. So what that ends up telling us is that this tree is what we like to call right heavy, which means that the height of the right subtree, which is this subtree over here that contains all these nodes, that differs by a height of more than one. In fact, it differs by a height of, let's see, 1, 2, 3, 4. There's 4 total heights, or the height of the right subtree is 4, whereas on the left there's absolutely nothing. There's zip. There's 0 height. And so we could see that the height differs by more than 1. Why don't we take a look at another example? If we insert D into our tree and we insert the nodes B, A, C to the left, similar how we did last time, and we insert F, so we start off with F as a right, then we insert E, and then we insert H. This kind of looks like our first tree, but how could we make this an unbalanced looking tree? Well, if we insert G as the left child of H, that's not unbalanced. We can see that the height on the left side is not differing by more than 1. It's actually less than, it's just 1. So because the height is equal to 1 and it doesn't differ by more than 1, we're good to go now. Even if we insert I to the right of H, we're still good to go because it only differs by more than 1. So even for node F over here, the height of the left is 1, but the height of the right is 2. So since it only differs by 1, we're good to go. It's only when you add J that you actually end up messing with the balance of the tree. And then you would have to somehow balance this tree to ensure that it is an AVL tree. So we're still maintaining the properties of a binary search tree, and we're trying to make sure that it's balanced. But what's the purpose of making sure that it's balanced? Why even bother with the balance of this tree? Why? Well, what's the purpose? So the purpose is that if we had this type of tree over here, this unbalanced tree, it kind of looks like a linked list if we ignore all these nodes over here. It kind of looks like a linked list, and so traversing it would end up being a runtime of OH, because the height of the tree will be the factor in that big O running time that causes it to be such a great running time. So what ends up happening is that it's bounded by this height. So we know that for an unbalanced tree, similar to a linked list, the worst case, big O, is O of H, because we are bounded by the height. And the height tells us how many times we're traversing that tree. So height tells us not how many times we're traversing, but the number of comparisons. Number of comparisons to find a target node, for example. Oops. Let's erase that. All right. What is our goal? Well, our goal for searches, as we listed in binary search trees, was O of log n. That's our goal. So with an AVL tree, we want to be able to take the log of n, or the number of nodes in the tree. We want to have a bunch of nodes, and that'll give us the height, but that'll be less iterations or less comparisons in the long run. So this is our goal. We want to reach an O of log n runtime, and the only way we're going to do that is if we have a tree like this one over here, where if we take the log of n, since there's 1, 2, 3, 4, 5, 6, 7 nodes in here, we know that if we take the log of that, that'll give us 2. So we know that in the worst case, we're only doing just 2 to 3 comparisons in between there to get or find a node. So before we even get started on like how to rotate these AVL trees, make them balanced and all that, why don't we focus on some of the terminology that's associated with binary or AVL trees. And so the first thing that I want to cover in this terminology section are balance factors. So balance factors, what's a balance factor? The balance factor tells us which way the tree is skewed or which way the tree is heavy. And so I know a lot of people, when you go online, they'll label the balance factors as heights, or how much each node differs in terms of height. I don't really like to do that. I'm more of a visual learner. So what I tend to do is I label them with forward slashes or backslashes. And so a forward slash is going to denote a left heavy tree. And we can see that this is kind of like an arrow pointing in the direction to left, but I don't like to make arrows because that's extra work. Who likes extra work? Anyways, if you have a backslash, then that's a right heavy tree. Once again, that's kind of going to the right, so we can that it's pretty easy to tell that indicates that it's right heavy. And then if we have just a dash, I know this is getting confusing because I use dash rather than bullets. Let me clean that up over here, make it nice and pretty. Then we know that's of equal heaviness. So we know that the subtrees are equal heavy. And so what does this tell us? Well, it's not going to make sense until I actually put it on a diagram, but if we go back up here to our unbalanced trees, it tells us how we want to label the tree to find out which direction it's unbalanced. And this will ultimately help us decide how to rotate the tree. So let's take a look at this example over here of this unbalanced tree to my left, the ACBDE one. If we start from the top, we know that the left subtree has a height of 0, and we know that there are more nodes in the right subtree. So we're going to say that the node A is right heavy. So if we put this next to every node, it'll indicate which side, either the left side or the right side, is heavier based on the height. We don't have to calculate the height. We'll get into that in just a second, but that will just indicate with a little notation what heaviness it is. If we look at C, we know that C is also right heavy, but B has no children, so we're going to label it as equal heaviness. We know that E is also right heavy, right? Because there's more nodes in the right subtree than or there's a height that's greater. We shouldn't say nodes. There's more height. It's a greater height in the right subtree than it is in the left subtree. So we're gonna put a right heavy for that. And D is going to be of equal heaviness. Same concept. Once we get to G, we notice that F and H, those both have a height of 1 compared to how far they are from G. So it's actually going to be equal heavy, not going to be right heavy. So you got to be careful when you're labeling these trees. All right, let's start with D. Let's start with our other tree over here. So what I'm going to do is I'm going to label from the top. We know that D is definitely right heavy because the height of the right subtree is greater than the height of the left subtree. So we're going to say D is right heavy. For B, we know that B is equal heaviness because A and C, they only have a height of 1 relative to B, and A and C are also going to be of equal heaviness since they're equal height. So when you're going down the tree, you take each subtree as if it's its own tree and label that node's balance factor like that. That's how you would label it. All right, so F. Well, F, it definitely is right heavy because the height of the right subtree is greater. E has no left or right child, so that's equal heavy. H has a greater right heaviness than it does left heaviness. There's more height in the right subtree than there is in the left subtree. G is of equal heaviness. I is right heavy because it has no left child, and J is equal heavy. So that's how you would label the tree. I know we didn't have a left heavy case, but you can just imagine that if we flipped the first tree that we labeled, this one over here, that tree actually has, if we just flipped it, that would end up giving us left heavy balance notations. And so another terminology that I just want to discuss is that it's not really a terminology, but you want to make sure you label nodes with heights. So you want to know what the height is for each node. So that's basically just going to be the max of the height of the left subtree, or the left, yeah, I would say left subtree is the best way to denote that, and the height of the right subtree. So we can do this to basically every node. Typically, the way I like to start is from the bottom and progress to the top. So if we start off with this one over here, let's choose another pretty color. Maybe orange isn't the best. Maybe we'll choose like a bright green to label our height. So I'm going to zoom in over here on this tree. And so let's label the heights. We'll start from node H. H has a height of 0, so we're just going to leave it at 0. And F has a height of 0, so we're going to say height is 0. G is going to be the max between the left and the right subtrees. So we know that both of them had a height of 0, so if we add 1 when we go up, we could say as we're going up, we add 1, that height is going to be 1. We'll put them in little circles so it's easier to separate. As we're going up, we'll add 1 to the height, and we know that D has a height of 0 relative to the rest of the tree. And E, well, E is going to be 1. 1 is going to be the max of 1 and 2, and so we know that E is going to be of height 2. B, once again, 0, because it doesn't really have nodes to the left or the right, so we can just say that that's kind of like a leaf node. So I would say that's a height of 0. And C is going to be the max. If we go up, as we're going up, we're adding 1 for each branch. It's going to be the max of 1 and 3. So we could say that C has a height of 3. And we can say A, if we add 1, A is just going to have a height of 4. There's nothing to the left, so you would just be comparing max of 0 to 4. So you may have labeled it differently. It all depends on how you were taught it. I was taught to label it this way, but it really doesn't matter as long as your heights can tell you whether the tree is unbalanced. That's where it really comes into play. We're also going to try to label this subtree or this tree to the right. So why don't we start off with the bottom once again? That's obviously going to be a height of 0. As we're going up, we're going to add 1, and then I has to find the max of 0, its left height, and 1, its right height. And we all know that 1 is greater, so we're going to label that with a height of 1. G has no height between it's basically just a leaf node, so you can just consider it as having no height in the left or the right subtree. So then H, well, H is going to compare the max of, as you're going up, you're going to add 1, the max of 1 and 2, and that's going to end up giving you 2. And as we go up, this is going to be 0 once again. You're going to add 1, and we're going to do max of 1 comma 3, which is just 3. As you go up once again, you're going to add 1, and you're going to do max of, well, there's a height of 2 over here. We didn't even get to that, so this is going to be 0. This is going to be 0. B is going to do max of 1 comma 1, which is just going to be 1, because as we're going up, we're adding 1s. And then D has to decide between max of 2 comma 4, and it's going to choose 4. Alright, so that's how you would label the heights of the tree. Now let's actually get into the rotations. Okay, so how exactly are we going to rotate these trees? So let's talk about that next. So in the case of There are four different cases that we can label, and this might be different from what you see online because I actually took what's online and and sort of flipped it because it makes more sense to me. But it's all up to you. It really depends on it's all up to the way that you interpret it. So there's four cases that I typically like to look at for rotating. And in class, you may have learned rotate case one, rotate case two, rotate case three. Not the ideal solution for rotating AVL trees. I don't really like that. We're just going to call them by their names. So the first one is an LL rotation, or what we call a left rotation. So this is when you end up rotating the tree to the right because of the way that it's skewed to the this is sorry, you rotate the tree to the left because it's skewed to the right. So typically what I tell students is that you kind of want to rotate in the opposite direction. So imagine we had a tree with A and it has a right child of B, which has a right child of C. First thing we do, label balance factors. So we can go ahead and label our balance factors. We know that A is right heavy, B is also right heavy, and C, well, C is going to be of equal heaviness. And so what we can see here is that because it is right heavy, or if we get the heights into the equation, this is height 0, this is height 1, and this is height 2, and there's nothing to the left, there's no height to the left, we know that it's unbalanced. It differs by more than one. And so, just so people don't get confused, that's a node. Since this is so skewed to the right, we end up doing a left rotation. So what that ends up looking like in this LL case is you end up making the tree B, A, C. And now it's balanced. And so notice that we've maintained the property of a binary search tree. Everything to the left is less than the root, and everything to the right is greater than the root. Let's take a look at the right rotation case. Let me add some separation up there. And if we look at the not necessarily right rotation, but right rotation case, or RR, and what that ends up looking like is you have a C at the top, a B to the left, and an A to the left. Notice that this is a binary search tree. We are maintaining those properties. And we're going to start by labeling our balance factors. So our balance factors have been labeled. Let's also throw our heights into the equation over here. And what we end up getting is what we end up noticing is that it's skewed to the left. So in order to fix this, we kind of just take that middle node again and we rotate it to the right. Well, how do we know that it's the middle node? I know I didn't explain this with the left rotation, but you know that's the middle because you take the second node and you rotate on that one because that's where it really has that height difference. Or like it has a height difference of more than one at that root of A over here. So you go down a level and you rotate on that node. That's the way I like to look at it because that's going to give you the rotation that you want. So you have B, A, and C. And so we know that these are all equal heavy. All right, what about our third case? Well, our third case, very simple. This is where it gets a little complicated, but it's still fairly simple if we do things my way. And that's not just a left rotation, but a left-right rotation. So left-right rotation. I like to call this case LR. What does LR mean? Well, if we draw a tree that's still unbalanced, remember it has to just differ by a height of 2. We have C, A, and B. All right, well, let's look at these balance factors here. C is going to be left heavy, A is going to be right heavy, and B is equal heaviness. And so you're wondering, I can't really rotate the way I was rotating before. What do I do? Well, if we start from the bottom, once again, that's 0, 1, and 2 for our heights. And since it differs by more than more than one in our left subtree, what we end up doing is kind of the same steps. Remember how I told you rotate in the opposite direction? Well, since this is right heavy, this is why I kind of made you do that in the notation way, not necessarily the height way. Since this is right heavy, you don't even really have to think about it. You kind of just rotate to the left. Hey, I just rotate in the opposite direction. Go from bottom to top, sort of like how I did with the rights, and you rotate to the left in the opposite direction. So now we have a C, B, and an A. And these are all left heavy, and that's equal heaviness. This ends up being case RR, as we saw up here. So we can see that this is no different than the RR case, or the right rotation case. And so what we end up doing is we rotate on this middle node again, and hey, look at that. We get B, C, A. We rotate in the opposite direction based on that node, the B node, that one in the middle. All right, and our last case is very similar to the one that we just did. It's called a right-left rotation. It kind of just looks like the inverse of this. So RL case. And let's take a look at what's going on over here. So we have A at the top, and we might have C as the right child of A and B as the left child of C. And so if we start from the top, we have right heavy, then left heavy, then equal heaviness, same heights as before. Same thing as before. You kind of just look at this node over here, the C. You know that it's unbalanced at A, so you go down, you look at this one, and you rotate in the opposite direction. Since this is left heavy, we're going to rotate to the right. So that's A, B, C. What does this look like? Well, this is basically case LL, or the LL case. And so not too different. We can label our balance factors again, and we notice that we rotate to the left in the opposite direction once again. So now we have B, A, C. And that's really it for AVL tree rotations. It's not more than what I just described over here. So we have our LL case where we rotate to the left because it was skewed to the right, or it was really right heavy and differed by a height of more than one. Right rotation is just the inverse of the left rotation, where you rotate to the right rather than to the left because it's left heavy and it's skewed to the left. Left-right rotation, that's where things start to get a little tricky, but it's not too bad. You're just making sure that you can somehow get back to case RR. And so you start off at the root where it's left heavy, and then the next node is right heavy, and you know that you have to rotate in the opposite direction each time. So you rotate A to the left, and you rotate B to the right. And then RL, where you have a right rotation and then a left rotation, or right heavy, left heavy, and then you know that you just rotate to the right and then rotate to the left, and you get your final answer. So hopefully that helps with AVL trees, but I'm a strong believer that you won't understand it until you actually try to go out and do some practice problems. So why don't we start by why don't we just try to do 3 practice problems, nothing too crazy over here, but just to test that we really, really understand what's going on. So why don't I start off with practice problem number 1. And practice problem number 1 is actually a really interesting question. This is going to make you get creative. So what I want you to do is draw a 7-node tree that needs to be rotated once. So that's a 7-node tree that needs to be rotated once. So try to get creative. Remember that our LL and RR cases are the ones where you rotate only once, whereas LR and RL are the ones where you rotate twice. So why don't you pause the video for a second and try to attempt this. Give yourself like 5 minutes, and then come back and see the solution. All right, so now we're going to look at the solution for this, and the tree that I ended up coming up with, or like how I thought of the tree, it was more like this. I was like, I knew I needed to have either a right or a left rotational case. So what I did is I knew that since it was 7 nodes in total, that I would have to have a tree that at the end kind of looked something like this. So I kind of thought about my end result first, and I was like, okay, well, if there's 7 nodes, I know that if I only have one level or a height of one, then that's already 3 nodes. And so if I want a height of two, then that's where I get a tree with 7 nodes. And so if I want to build a tree that needs to be rotated only once, and then this is sort of my end result for the tree or what my tree might look like, I ended up drawing a tree where I just modified it so that I had to, where I was forced to rotate once. And so I ended up doing, for mine, I ended up doing a right rotation. So I drew a 7 over here, and I was like, well, what's the best thing I can do? And that's 6 is the left child of 7, and 5 is the left child of 6. And so if I go and I label my balance factors, I have left equal. So I knew that it was unbalanced here. I can label the rest just to show you that the rest was okay. So we have right and left and then equal. And a lot of you are probably like, well, why don't you do a right left case? Well, node 4 isn't the one that's unbalanced, right? So node 4 isn't unbalanced. It's actually node 7 because it has no right subtree, but the left subtree has a height of 2. So as a result, you need to rotate at node 7 being the root. And so because of that, I ended up rotating to the right. I ended up getting the tree where 6 was the new root, 5 was the left child, and 7 was the right child. So how I would do this, once again, is I would kind of just play around with it. Think about what I want my end result to look like. Just think about how trees work in general and how a 7-node tree at the end just needs to, a 7-node tree just needs to be complete. Like a 7-node tree will be complete at the end. And so as a result, I drew a tree like that. Another way to look at this might be to just think, okay, well, I know I need to do either a left or right rotation, so I might just try to draw that first and then build on top of it. So I might have drawn like 2 1 0 first, and then try to build other nodes on top of it to make sure that the right or the left side was heavier than the other sides. So you really just got to play around with it. Why don't we try to do another practice problem that's kind of similar? I'm going to change over to a purple over here. And this is basically the same, but in practice problem 2, what I want you to do is I want you to draw another 7-node tree that you actually have to rotate twice. So draw a 7-node tree that you need to rotate twice. All right, so pause the video, try to attempt this. All right, so let's take a look at my solution. So what I ended up coming up with was very similar to my last problem. I was like, okay, well, I kind of just need to switch. Oops, I kind of need to switch the ordering of the nodes. So instead of 7 having a left child of 6, I said let it have a left child of 5, and then let's add something that's between 5 and 7, which would be 6, as the right child of 5. And that would have given me an LR case, where at the top, if we label our balance, I'm going to label it with a different color to differentiate. We have right, left, right, and equal for that right side. We have equal, equal, equal for the left side. And so the way I want you to look at this is, hey, I know that technically you're very, very tempted, once again, to look at this and rotate it at 4. But that wouldn't make sense because remember, 4 does not have that height difference of more than 1. It doesn't have, there's not another right child to 6. which would have caused that. Instead, it's node 7 that has no right children, and it has two left children, which are end up causing it to have a height of 2, even though it has no right children. And so it's unbalanced there. So because this is a right-left case, I'm just going to rotate it like so. I'm going to rotate to the left first to sort of counteract that right heaviness that's in the tree. And what do I end up getting? Well, let me switch to my purple over here. I get a 4 at the top. That doesn't change. And then 2, 1, 3. That doesn't change at all. And then I get a 7, right? And I get a 6. So 6 ends up being the root. And then 5. And then this is basically the same as the last problem where we just had a right rotation case. So this is a right rotation case. And so what I can do is I'll go ahead and label my balance factors again. We have right, left, left, equal heaviness, and equal, equal, equal heaviness. And so if we were to just balance this again, all we have to do is rotate to the right on 6 because it's left heavy. And so we have 4, 2, 1, 3, 6, 7, 5. And that's how you would rotate that tree. All right? And that's balanced and all that. For our last problem, we're going to take it step by step over here. And this is going to be an interesting one. I'm going to use my favorite color, pink. So practice problem 3. Let's go. So what is this? What ends up happening over here? Well, I'm going to start off with a tree. 5, 2, 1, 3, 6, and 7. What I'm going to do is I'm just going to go ahead and start to insert nodes and see how it changes the tree. So why don't we start off by inserting an 8 to the tree. If I insert 8, if I have node 8, I have to compare 8 to 5. 8 is greater than 5. 8 is greater than 6. And 8 is greater than 7. And so I ended up making it a right child to maintain that property of a binary search tree and inserting it to the right of 7. Actually, what I'm going to do here to clean it up is I'm going to write it step by step. So problem A was insert 8. So there's multiple parts to this. What I'll do is I'll copy this tree and I'll put 8 to the right since I showed you how that looked. And so what I want to do is start off, just make all my balance factors. That's equal heaviness, and then that's equal, equal, equal. Remember, really right heavy because there's more nodes to the right than there are to the left at each of these cases. Since we have this right heaviness and then right heaviness twice in a row over here, we go down to level 6 and we rotate on 7. And so it ends up looking like 5, 2, 1, 3, then 7, 6, 8. Yay. So next thing that we're going to do is we're going to try to insert a 10 and see how it impacts our tree. So what I'm going to do is I'm just going to copy the tree over from last time and I'm going to insert 8 was in there. Actually, this is the wrong tree, so why don't I erase that, go back up over here, copy this, just do a little copy pasta action, and I'm going to put 10 as my right child of 8 because I wanted to insert 10. Well, how did I get 10 as the right child? 10 is greater than 5, which is greater than 7, which is greater than 8, so it ends up being the right child of 8. That's how I got it. And so what we're going to do now is label the balance factors. So I have right heavy right heavy, right heavy, and equal heaviness. 6 is equal. This is equal, equal, equal. This is meant to trick you. So why is this meant to trick you? Well, this is meant to trick you because you have two right notations in a row to indicate that it might be a right or a left rotation, but in reality it's not, because the heights don't differ by more than one at any case. So if we're at 5, the heights don't differ by more than one, right? 7, the heights don't differ by more than one. 8, the heights don't differ by more than one. If we look at these left and right subtrees, we notice that these heights don't differ by more than one in either case. So we're actually good to go. This was good. This was good. Yay. What if we insert 0? What happens if we insert 0? So why don't we take a look? I'm going to take the previous tree, put a 10 here from last time. If I insert 0, well, what is that going to look like? I compare 0 to 5, it's less. 2 to 0, that's less. 1 to 0, that's less. So I end up making it a left child of 1. And once again, you can label your balance factors. They end up being equal for 5. 2 ends up being left heavy. 1 ends up being left heavy. And 0 ends up being equal heavy. 3 is equal heavy. 7 is right heavy. 8 is right heavy. 6 is equal heavy. And 10 is equal heavy. But just because you have 2 of those notations in a row doesn't mean you have to actually rotate. Remember, it doesn't differ by height of more than 1 again, so you're actually good to go. You're chilling. All right. Last but not least, we're going to take this tree from before, and at this point, I think everyone understands how to label the balance factors in the tree. What I'm going to do is I'm going to insert 9. So what happens if I insert 9 into this tree? Let's take a look. And what ends up happening is I have a 9 node, and I'm going to take it, and 9 is going to be compared to 5, that's greater. Compared to 7, that's greater. Compared to 8, that's greater. Compared to 10, that's also greater. So it ends up being, that's also less than, sorry. And so it ends up being the left child of 10. All right, well, if it ends up being the left child of 10, how does this affect the balance factors? Well, it only changes in really one location, that's for 10, where 10 is now left rather than equal heaviness, and 9 is of equal heaviness now. And so what ends up happening? Well, we notice that 8 is that node that is unbalanced. And so because 8 is, 8 is, so 8 is that node that's unbalanced, but even before that, 7 is unbalanced. So what is 7 going to do? Well, 7 is going to be like, yo, we have to rotate this tree. We have to balance this tree. So let's go down and figure out, where do I start my balancing? It definitely can't be at 7. It doesn't make sense if we rotate at 7. What we have to end up rotating is at 8. Remember, we go one level down and we start our rotation there. We notice that we have a right and left rotation like so. So what do I do? What I do is I actually end up rotating the left to the right. I rotate in the opposite direction. And what does the tree I end up getting? Well, let's take a look. So we have 5, 2, 1, 3, 0. And then we have 7, 6, 8, 9, and 10. And so we can see this is very much just a left rotational case. And so if I rotate right, equal, left, equal. So I redid all my balance factors, and I see, since 7 is the one where is the culprit over here, I guess, it's unbalanced over here, we go down that level, and then we do our left rotational case because it's right heavy. And so we rotate on 9. And in the end, we end up getting 5, 2, 1, 3, 0. All right. And over to the right, we end up getting 7, 6, not 8 there. Since we rotated to the left, we get 9, 8, and 10. And if we were to check our balance factors just for good measure, we get right. We get right again. We get equal, 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 equal. Sorry, not equal there. It's left, equal, and left, and that's it. So, that's it for AVL trees. Alright, I hope you enjoyed that video. Don't forget to smash that like button. Leave a comment down below if you want to see more content like this. And hit that subscribe button with the bell notification to know when my next video is out. Hope you have a good one, stay safe, and I'll see you next time.